So when you see a title this long, it usually means there's some confusion. And the confusion here has a root cause. The root cause is I'm very interested in thermoelectrics, but in the course of the project, I encountered some really interesting system-level phenomena that made thermoelectrics energy harvesting extremely difficult to do. So I'm sure if you see confusion in the name, you'll probably see a little bit of confusion throughout, but I'm going to do my best to keep it a little bit clear. Okay, so the motivation, most people in energy harvesting know that ZT has sort of been really limited, dominated by these compound semiconductors that have the best characteristics. But if you'd like to integrate a harvester with a silicon chip, then you should probably start with silicon. The only issue being that the ZT, which is the dimensionless figure of merit for thermoelectrics, for silicon is about 100 times worse than the compound semiconductors. Plus, when you're building a harvesting system, you need to control the flow of heat. So you want all the heat to be collected from the heat source, go through your harvester, and be rejected at a heat sink. So you have to consider the range of thermal conductivities of available materials, right? And of course, you also need to look at probably inexpensive materials. So the approach that we took in this project was to look at something in the literature that we found very intriguing, in which silicon nanowires were shown to actually have a ZT that's competitive with compound semiconductors. And the simple reason is the thermal conductivity is lower when you nanostructure silicon. The acoustic phonons collide with the sidewalls much more than they collide with each other, and so the thermal conductivity goes down. But the bulk thermoelectric properties, the bulk resistivity, still are maintained. Okay, so what we actually did is to use a 65 nanometer commercial high volume CMOS process. In fact, it's on 300 millimeter wafers. And we built a device where the active region that is ordinarily what you would use to build a transistor, or this could be, say, an N-well tap or a P substrate tap, we used as a vertical thermopile. So we would have a heat source that's coupled up through the metal system. It goes, in this case, we used a resistor to emulate a heat source, although in the packaging, in a real implementation, you would build maybe a highly interdigitated, capacitor type, MIMCAP type structure to pull the heat from the outside into the top end of the thermopiles. And so you have your N-type thermopile here. So there's the hot end, and this is the cold end, because your heat sink is basically the silicon substrate, and somehow you've managed to make a good thermal contact to that, to the outside world. And the objective of designing this device is to get as much of the temperature drop as possible to happen across this 1/3 of a micron tall thermopile. So here's a photograph of the devices that we built. This is a layout picture. Okay, so let's keep going. So it's probably preaching to the choir a little bit to talk about the physics of thermoelectric generation, but basically what's happening is that hot electrons and holes diffuse out into the semiconductors, and basically if you have an open circuit configuration, that results in a Seebeck voltage. Okay, so the way that we measured these little devices, of course these are too small to be able to put a physical thermometer on and expect it to be at all accurate. And of course you have a very non-uniform temperature profile, so it would be very difficult to use any sort of ex situ thermometry to study them. So we used something called the hot wire method. In the literature you might also see the 3 omega method. And the difference really between those two, as far as I could tell, was that the hot wire method is more of a DC type of method, and the 3 omega uses a locking amplifier to look at the third harmonic. But basically what happens is this resistor that's providing heat to our harvester is itself getting hotter, and its resistance has a temperature coefficient. And if you work through the math, you'll have basically odd powers in the IV curve. So that hence the 3 omega method if you use a locking amplifier. But the way that we use this is simply to take an IV curve and just fit it using a simple least squares method. And that actually was a very reproducible method. In fact, going across the 300 millimeter wafer, we had 5 to 10% parametric variations. This is if you find a way to actually use this, it's a highly manufacturable type of device, because you're simply building an N-tap and a P-tap, which you ordinarily build all over the place in your circuits. Okay, so one thing that's very important when you have this device with really high thermal gradients and temperature variations inside the device that you want to understand is your simulation and your modeling. So for simulation, we used the gradient design automation package called Gradient. And using this, we were able to convince ourselves that we dropped, in our very best layouts, we dropped about 50% of the temperature across the thermopiles. But once you want to do some analytical work to say understand how, what's the best thing you could ever do in a system, or if you put this into a product and you want to develop a SPICE model to represent it, you need to do some pencil and paper analysis too. Okay, so without going through all the equations here because we don't have an hour, you have to write down the thermal equivalent circuit, which includes the phonon thermal conductivity, and you can write down the heat flow through the electrons and holes in terms of the Peltier effect. A little bit of that is siphoned off into the electrical equivalent circuit, and it appears as a battery representing the Seebeck effect. You also have resistances of the device, and you have a load resistance. And you can write all these down and get your characteristic device physics equation, which is basically for the power delivered to the load, and it goes as the square of the temperature difference. So just like with CMOS, we've got a square law, and so designers will be happy. The algebra doesn't have to be changed. If you find the optimum load resistance to deliver max power, it's simply the conventional matching constraint. You have if the load is the same as the internal resistance, you get the max power transfer, and then the max power becomes this. Okay. You also need some hooks for the system level analysis. So the really important thing with thermoelectric energy harvesting is you're converting heat flow to electricity. So you have to analyze what the heat flow is through the device and write down an expression for it so that you can plug it into the system level parasitics. And you also need to think in terms of the thermopile thermal impedance, because every heat sink will have a thermal impedance, every heat source will have a thermal impedance, and that's going to end up limiting what you can do. These are just some demonstration characteristics on one of the early devices. You can see that there's a reasonable load line characteristic when you put it against a current source in a 4156 analyzer. You can see there's a square law. Actually, this is a log-log plot of a square law, which is a white line, against the actual harvested energy over several orders of magnitude. So the square law approximation is pretty good, but not perfect, a lot like in the case of a MOS device. Okay, so just kind of zooming into one thermopile. So this is a little ridge, 80 nanometers wide, 365 nanometers tall, and 750 nanometers long. Each of the complete devices is a large array of these, and there are a lot of ways you can lay it out. Of course, I tried laying them out in many different ways, and actually it gives me a way to continue to study the parasitics, which hopefully I'll do a paper at next year's conference, especially because Spain will be a really nice place to go. If you look at the measured data from one device, you can measure the resistance of the device itself. That's the resistance through the parallel array of N-type and P-type thermopiles. There's a thermal impedance that you calculate by measuring that nonlinear IV curve of the heater resistor. And then there's the open circuit voltage, which you've obviously just measured the voltage that comes out. And you can scale all this to 5 degrees C to get 1.2 millivolts out. So you can start drilling down through and pull out the geometric factors and come up with your effective resistance per thermopile, which includes some parasitics, and then your effective thermal impedance per thermopile, which is a big number, and it also includes the parasitics that we haven't really developed a way to extract yet, which is why there's some further research to be done. And then you can come up with an effective Seebeck coefficient, knowing that you've also got a temperature divider in the circuit. So this is not your true material Seebeck coefficient, this is a device level Seebeck coefficient. So now let's just do a thought experiment. Suppose I have a delta T of 5C, so I want to make a watch that powers itself. Can I actually power a watch with this device? And of course I'm going to be a lazy designer. I want 2 volts, right? So let's see what we can do. So how many thermopiles do I need to make 2 volts? Well, that's about 5,000. If I have this thermal impedance with that many thermopiles, then I end up with an array that has 68 C per watt, which actually is not a terrible match to what I think a watch would have, at least on the skin side. On the air side, it might not be that optimistic. And then the resistance is around 10 megohms, and when you plug it into the characteristic equation, it's about 100 nanowatts. So that might not quite power a watch. So it's, it is silicon after all. So So how good was our nanostructuring? Did we actually, we didn't quite close the gap with bismuth telluride, but we did move the needle a little bit. So this is an experiment where I have a whole series of different layouts. I have layouts that have very thin, the smallest I can make, 80 nanometer thermopiles, and then I have layouts that have 240 nanometer thermopiles, but fewer of them, and it's all arranged so that they have the same resistance. So you can look at the measured resistance, and across this array of devices, it was about the same. And the power for the most nanostructured devices is definitely higher than the power for the big devices. But you can see this is not 2 decades. This is maybe a factor of 3. So, it's. I think we made an improvement. I haven't really seen another device-level demonstration of the nanostructuring effect. I've seen some really brilliant laboratory science using special instruments to characterize nanowires, but here we put this into devices and shown basically the same thing, but on not as extreme a level. So basically the concept worked, and if you could actually build nanowires with this process, if you maybe changed the mode etch process so that you could actually draw a tiny circle, you might actually be able to do even better than this. Okay. So once you have a technology, well, you want to look at, how could I actually implement this? So you have to look at the parasitics that exist in the system. So there's going to be a series thermal impedance, and then obviously, especially if you have a very, miniaturized device, there's a leak term as well. So that you have to consider. So basically, once you solve this resistor divider and also do the same optimization that you do for the load resistance, you'll find the factor of a quarter turned into 1/16th, and sure enough, there's a matching relationship that the best kind of thermopile array size, as given by its thermal impedance, is the parallel combination of the series and link terms. So it's a nice simple algebra, and this allows you to start playing some games with kind of what-if experiments. Oh, and I did some analysis of a variety of different layouts and just fit some general characteristics using this equation. And it seems to describe the behavior fairly well. That's not too surprising. Okay, so suppose I have an ambient harvesting system. So I have an ambient 5C difference sitting at 300 Kelvin, and I've got a range of devices from bulk silicon at 0.01 out to a nice, bismuth telluride compound semiconductor device at 1. And then I've got some different thermal impedances. So this is the best harvesting that I can do for a given set of thermal parasitics, right? So for a wristwatch, probably 100 C per watt, and about the same leakage is about the best that I could imagine when I just sort of drew some pictures and did some scratch calculations. So this is the dotted line. So this is really what we're playing with. So the device that I built is probably somewhere in this range. So, the 100 nanowatts that I calculated, with more parasitics is kind of in the range of what I would start to expect. For some of the more optimized materials, and if you have a system that really minimizes the leakage parasitics in particular, you might be able to get in the sort of single digits to just over 10 microwatts type of harvesting. So, these are just some of the design concepts that you're going to have to use if you're going to do ambient harvesting. Okay, so system level performance. So, looking at some of the more general characteristics, as I change the packing fraction of my device, so it actually is a relatively low density, even though the Eagle's View layout picture looks like it's very dense. This is only a 5% packing fraction when you really look at the details. So going down to 0.2%, you can see that sure enough, the power generated does have an optimum as a function of the packing fraction, which is controlling the thermopile array thermal impedance. And so to conclude, as far as I can tell, this is the first time that device data has demonstrated the benefit of nanostructuring silicon. This actually, because these are so small, we can actually probably do a fair amount of voltage stacking. And I think this may be a novel feature of this technology as well. But because it's so small, it requires a high density of heat flow. So if you talk about building a system, well, now you have to collect the heat, concentrate it, run it through the converter, spread it back out to the heat spreader. So there's some non-trivial issues, but there are some cases where a concentrated heat source may be of interest. Advanced CMOS makes it really easy to do a slab, but there are area constraints in addition to the width constraints, so it's not entirely trivial to do a true nanowire, although I think with some research you probably could. By the way, there's also locate dielectric in these devices, so it allows you to choose where your temperature drops are. So you can actually do a little bit better than you could if it were all encased in a high-density TIOS or full density of SiO2. When you're building the system, obviously you need to consider the material ZT, but then you can define ZT at the device level as well, and this can be important. Then you need to consider all the thermal engineering of the full system. Okay. All right, thanks.